Welcome back everybody. This is our video solution to problem 5 from Quiz 2, Math 307, and during fall 2023. This is linear algebra at Cal State Fullerton. In this problem, we are given a list of vectors, and we want to determine whether or not this list is linearly independent inside of R3 viewed as a vector space over the real numbers. So I want to show you a couple of different approaches that you might take to solve this problem. The first just goes right to our definition of linear independence and then a subsequent theorem. So our definition of linear independence was that a list is linearly independent if every element in the span of that list has a unique representation. That's a lot of things to check. So we had a theorem which says that, and let's write it here, it's enough to show. So if I give a name to this list, by the way, let me just call this list L. L is linearly independent if 0, okay, so the 0 vector in R3, by the way, right, is 0, 0, 0, has a unique L representation. Okay, so it turns out it's enough to just check the 0 vector. You don't have to check every other vector. So what would that mean here? Well, we know the 0 vector always has the trivial representation, where you just write down 0 times each of these vectors and add them up. That'll certainly give you the 0 vector. But we want to show that's the only one. So what I would do is I'd say assume I have real numbers A, B, and C. Why reals? Well, because we're looking at a vector space over the reals, such that the 0 vector, 0, 0, 0, is A times 0, 1, 1, that's the first vector, plus B times 1, 0, 1, that's the second vector, plus C times negative 3, 2, negative 1. All right, and we want to show, we want that A, B, and C are all equal to 0. Because that would show we have a unique representation. All right, but we can use this to get a system of equations. Okay, so this is what we want. But let's just distribute the A, B's, and C's and add everything together. So in the first component, I get A times 0 plus B times 1 plus C times negative 3. So that's going to give me B minus 3C. In the second component, I get A times 1, B times 0, and then 2 times C. So this will give me A plus 2C. And then finally, in the third component, I get A times 1 plus B times 1 plus C times negative 1. So this is A plus B minus C. Now on the left-hand side, I have 0, 0, 0. And on the right-hand side, well, I have this more complicated expression. But if I have two triples in R3, they are equal if and only if each component is equal. So this gives me a system of 3 equations with 3 unknowns. So first I have that B minus 3C is equal to 0. Then I have that A plus 2C is equal to 0. And then finally I have A plus B minus C is equal to 0. So notice I'm just equating each of the components. That's how I get this system. And so now we just need to go through and see if we can solve it. And there's, again, a variety of ways of doing this. We could use elimination of variables. We could substitute things. We could go to a matrix form. We could do like a reduced row echelon form of this thing and see if we can solve it that way. I'm going to take the way that always feels the most natural to me when things aren't too complicated. I'm just going to try to solve these equations and substitute into other ones and see what happens. So, for example, this top equation, I can solve it for B. I get B is equal to 3 times C. And this second equation allows me to solve for A. I get A is equal to negative 2 times C. And so now substituting into this bottom equation, I can replace A by negative 2C. I can replace B by 3C. And of course I still have a minus C. And, oh, what just happened? Well, this is supposed to equal 0, but yeah, I mean, sure enough, it does equal 0. 3c minus 2c minus c. Yeah, that's already 0. Like, this wasn't actually helpful here. Now, in your previous course on linear algebra, you might have seen situations like this happen before. And when you do, it might make you think, wait a second, I don't know that this is actually going to have a unique solution. Right? Whenever you would have this, and in fact, what just happened? Like, why did we end up with this? Well, what if we put just a little dividing line here and add these two equations? Notice A would go to A, B would go to B, and negative 3c plus 2c, well, that is negative c. So actually, this third equation didn't tell us anything new. It's not actually a restriction. So what that means is that I can write down an infinite number of solutions, and all they have to do is satisfy these top two equations. I can pick any c I like. So the solutions to our system are going to be all things of the form. Right, so all things of the form. So the A should be negative 2 times the third component. The B should be 3 times the third component. And then I can pick any third component I like. So C can be any real number. So we just pick a real number. Now if I pick C equals 0, then of course the A and the B are both going to be 0, and that gives me the expected trivial representation. But I don't have to let C equal 0. What if C is equal to 1? If C is equal to 1, then I'm going to have A is equal to negative 2, and B is going to equal 3. And you can check. If I let A be negative 2, and I let B be 3, and I let C equal 1, then I get another representation of 0, right? Check the first component, negative 2 plus 3 minus 3. Oh, you get 0. You can check the other components. It works. Okay, therefore, 0 does not have a unique L representation. But that means that L is linearly dependent. So 0, 0, 0 does not have a unique L representation. And therefore, L is linearly dependent. Okay, so that solves the problem. Now, we had to do quite a bit of work. And I want to show you now a different technique that you could use. And of course, the tricky part here is, right, like you kind of have to gamble on what you think is correct, right? Do I think it's linearly independent? Oh, if so, then maybe this is the way I'm going to do it. But what if I think it's linearly dependent? Well, maybe I'm going to try to show that it's linearly dependent. And so let's go back up here. I'm going to make a little copy of our vectors. Make a little copy. Now let's move those down. And let's say that I really did believe that this was linearly dependent. And if I do believe that, then I know by the linear dependence lemma, that's what we call the LDL, that one of these vectors has to be a linear combination of the previous vectors in the list, right? Meaning the vectors to the left. So the only way the first vector could be a linear combination of the stuff to the left is if it was the 0 vector, because there are no vectors to the left of it. So that's not the one. So now I check 1, 0, 1. That to be a linear combination of the previous vectors, that would mean it would have to be a scalar multiple of 0, 1, 1, which cannot be. All right? If I take any scalar multiple of 0, 1, 1, this is going to be 0, A, A. And that's definitely not equal to 1, 0, 1 for any A. Because you can see the first component, they don't match. Okay, so already the first two must be linearly independent with each other. Okay, so that would mean if this was going to be linearly dependent, then the third vector would have to be a combination of the previous two. All right, so I'd like to try to show that negative 3, 2, negative 1 is some combination of 0, 1, 1 and 1, 0, 1. Okay. And again, I can use this to set up a system of equations. But I want to work more easily than that even. I'm going to work one step at a time. If I'm going to be able to show that -3, 2, -1 is a linear combination of the previous two, then it should work even in the first component. So I should be able to multiply 0 by something and 1 by something and get -3. And this is where I'm like, well, I mean, I don't care what I multiply 0 by, it's still 0. So what am I going to multiply 1 by? Oh, it's got to be -3. So I'm just going to actually toss a -3 as the coefficient here. Because no matter what a is, right, I have to use -3 so that these match up. Okay, so then I go to the second component, right? And I say, well, okay, what's happening in the second component? -3 times 0 is 0, but I want to get a 2 at the end of the day. Well, I can do a times 1 here. That's actually what I'm going to get in the middle component, so a has to be 2. Okay, so now I've matched up the first two components, and so I just have to make sure that everything works in the third component. And let's see. 2 times 1 is 2. -3 times 1 is -3. 2 plus -3 is -1. Oh my goodness, it lined up. Okay, so I'm just able to eyeball this thing and find the right linear combination. Okay, so this is kind of a clever approach. Again, you could set this up as a big system, all right, and you'll be able to solve it that way. Sometimes it's just a little easier to just eyeball these things one step at a time. Okay, so again, though, because we've written the third vector as a linear combination of the other two, this again implies that L is linearly dependent. All right, so hopefully one of those two approaches really helps you out. We will see you all next time.